is Nadine Dempers. I am currently a second-year vacation work student at Optimum Solutions. I am also completing my BSc degree in Physics and Mathematics at the Northwest University. In this webinar, I will be discussing predictive maintenance and specifically how a system can be implemented with MATLAB. Firstly, I'd like to clarify, every time I refer to maintenance, I am referring to the upkeep of equipment or keeping something in good condition. To illustrate the different types of maintenance, we'll look at a simple example, like your car. Some people might say, I'll cross that bridge when I come to it. This is the approach of reactive maintenance, when you only replace or repair components once they break or give you problems. This can become very risky. Others might say, rather safe than sorry. This is the approach of scheduled maintenance, where you routinely replace components on a regular basis. This can become quite costly, even though it does prevent failures from occurring. Today we will be looking at predictive maintenance. This combines the benefits of both reactive and scheduled maintenance by allowing you to get maximum usage out of each component without increasing the risks of failures. This is done by predicting when failures will occur on each component and scheduling maintenance accordingly. So why are we looking at predictive maintenance specifically? Well, it has many benefits. By predicting when failures might occur, you greatly reduce failure risks. You can also optimize processes that you use on a daily basis, thereby improving the productivity of your company. If you do all of this, you will definitely create a good reputation for your company. However, the main benefit is that you can drastically decrease costs. By reducing the number of failures that occur, you reduce the expenses on damage repairs, and you also spend less money unnecessarily replacing components that are still in a good condition. The problem with predictive maintenance is that it can become very complicated. Specifically in the data analysis part of the process, it requires working with very large data sets and multiple variables at the same time. MATLAB gives us all the tools we need in order to be able to handle these complex systems with large data sets and multiple variables. MATLAB is applicable for usage in many fields, including aeronautics, safe energy, industrial machinery, and health management, to mention only a few. Baker Hughes is a company that works with gas and oil extraction. They were experiencing regular pump failure on their trucks. This was problematic because each time a pump failed, they had to send extra trucks to that site. This was costing them a lot extra. So engineers at Baker Hughes made use of a predictive maintenance system using MATLAB. They used MATLAB to develop pump health monitoring software, which helped them to predict exactly when their pumps would fail and prevent these failures. By implementing this system, Baker Hughes experienced a 30 to 40% decrease in their expenses. The engineers also stated that MATLAB allowed them to develop the software a lot faster, and they were able to handle the datasets very easily. The example we will be discussing in detail today is about the turbofan engines on aeroplanes. Data has been collected from 100 turbofan engines. The engines were all in good condition at the beginning of the recording of the data. The engines were run for 125 flights, after which scheduled maintenance was performed on all of the engines. The sensors on the engines collected data on temperatures, pressures, flow rates, and speeds. We will use all of this data in order to try and predict when each engine might fail. This will be done using machine learning techniques. What is machine learning? In 1959, Arthur Samuel defined machine learning as the field of study that gives computers the ability to learn without being explicitly programmed. There are two main types of machine learning, namely supervised learning and unsupervised learning. The main difference between the two is that supervised learning requires both input and output data, whereas unsupervised learning requires only input data. Now for the Turbofan engine data, let's look at how both of these types of machine learning techniques can be applied to the data. For supervised learning, we will have to use data including data where failures occurred. This data will then be categorized into components, and machine learning techniques will be used to refine these categories. These categories can then help us to predict the time until failures will occur on each engine. This approach is considered very impractical in real-life situations, since it is not very easy to allow your engines to run until they fail. Failure data is also very expensive and difficult to obtain. For this reason, we will be mainly focusing on unsupervised learning for the rest of this webinar. For unsupervised learning, we'll consider the scenario where no failures occurred. So we'll use the data for the first 125 flights prior to the scheduled maintenance. We will then recognize patterns in this data set and use these patterns to develop a warning system, which can then in turn be used to increase the time between scheduled maintenance until we fully rely on our warning system to decide when to perform maintenance. So before we can apply these techniques to the data, let's first get an idea of what data we're working with. So here we read in the data for only the first engine into MATLAB, and this creates a variable. If we open this, we can see this is all the data for engine number 1. The time refers to the number of flights, and here we can see data for temperatures, pressures, speeds, and so on. So now that we have an idea what our data looks like, let's plot each of the signals against time to see how they vary for our first engine. So this gives us quite a good idea of what happens to the pressures and speeds, but it is not very useful in helping us predict when the engine might fail. So for this reason, we'll try something else. A control chart is very effective to see what normal data looks like and what abnormal data looks like. So here we have chosen arbitrary upper and lower limits for normal conditions. Those are these red lines we see over here. So all of this data is considered normal data. These data points that lie outside of these red lines is considered as abnormal data. So this is most likely where things started to go wrong with the engine, or we started experiencing problems. Now we can see that most of these data points lie towards the end, and we know that the engine was in a good condition at the beginning, so that means somewhere along the line, as it was running for more flights, things started to go wrong and the engine was most likely closer to requiring maintenance. Now this is useful when we're only looking at data for one engine, but since we're looking at data for 100 engines, we'll have to try something else. This is the workflow we will be using for the unsupervised learning approach on the data. Before we can apply machine learning techniques to the data, we have to prepare the data. So if we go back to MATLAB, we only have the first engine data available in MATLAB, so here we read in the data for the other engines, and the data store is used. Now the data store is very useful when working with large data sets, since it allows us to read only chunks of the data into the memory at a time instead of reading it all into the memory at once. Now we also use a tool array to read the data in. This is very effective when working with large data sets, seeing that any command containing a tool array is not executed immediately. It is only executed once the gather command is called. This is useful because we can now execute multiple commands while only running through our very large data set one time. Now that we have all the data available in MATLAB, we can plot the data in a similar way to the data for the first engine. So if we open up these plots over here, we can see that the data varies quite a bit for each of the engines, and there is no specific line that can be identified for any of these signals. For this reason, we can't approximate the data using only a few of the engine's data. We have to use the data for all 100 engines. So now, before we can apply machine learning techniques to the data, we have to standardize the data. This is done by setting the mean to 0 and the standard deviation to 1. Now what this does is it expresses the data in terms of standard deviations from the average instead of in terms of different scales and units. This means that all of the data is now uniform and ready for machine learning techniques. So next, we can apply principal component analysis to the data. Now what is principal component analysis? Firstly, we'll start off with our data represented on a set of axes, with each axis representing one of the variables. Then we'll determine the first principal component. This is a straight line through the origin in the direction of maximum variance. So here we can see that our first principal component is the best straight line approximation for our data. To further increase the accuracy of this approximation, we'll determine the second principal component. Now this is orthogonal to the first principal component in the direction of maximum variance. These two principal components now serve as an orthogonal basis set, which we can use to determine where unknown data points would lie. So if we go back to MATLAB, we can apply principal components analysis to the data, which will allow us to work with fewer dimensions, which is a lot simpler. Here MATLAB also draws up a plot of the principal components and how much of the data can be explained by each principal component. So here we can see that if we use the first principal component, almost 80% of the data can be explained. If we use the second principal component, just above 10% of the data can be explained. Now this decreases for the higher principal components. However, if we use the principal components cumulatively, if we use both the first and second principal components, we can explain almost 90% of the data. If we use the first, second and third principal components, exactly 90% of the data can be explained. Now this increases the more principal components we use. But since we want to work with a smaller dimension set, we'll try and use fewer principal components. Now here MATLAB will draw up more plots for us to investigate which principal components would be the best fit for our data, but for this webinar we'll simply assume that the first and second principal components are the best option. Now here we determine the contribution of each signal towards the principal components in order to give us an indication of which signals will be important in identifying problems with the engine. Since all of the signals have a similar contribution towards the principal component, we'll have to consider all of the signals when trying to predict failures in our data. So now that we have applied principal component analysis to the data, the next step is to recognize patterns in our data. Seeing that we will be drawing up a lot of plots to recognize the patterns, we take a sample of the data, since it is not necessary to use each and every data point in all of our plots. Next, we'll determine the first and last data points for each engine, simply because that's an easy way to see in which direction the data progresses. In this section, we plot the first and last data points for each engine. Now, if we open up this figure, we can see that the first data points lie in this region, whereas the last data points are fairly spread out. Now initially we'd expect that the first data points all lie in one region and the last data points in another region, but it actually makes sense that the first and last data points overlap. Now we assume that since we know that at the beginning of the recording of the data all of the engines were in good conditions, that data points in this region indicate that the engine is under normal conditions. So now these data points for the last data points for each engine that fall in this region could indicate that when maintenance was performed on the engines, the engine was still in a good condition. We know that scheduled maintenance was performed on all of the engines, irrelevant of what condition they're in. So we can assume that this region indicates normal conditions for the engines, and data points that lie further out might be an indication that problems are starting to occur and the engine might require maintenance. To further investigate this, we'll consult our maintenance team. And in this case, the maintenance team has identified that engine number 39, 57, 70, and 91 were giving problems at the time of maintenance. So we plot the last 20 data points for these 4 engines in red, and we'll see in which regions they lie. Now, this corresponds with the assumptions we made earlier on, seeing that all of the data points for the faulty engines lie on these outer regions, and none of them lie in the beginning. And we can further see that since these are the last 20 data points for the faulty engines, that the engine started in a good condition and progressed towards worse conditions. To further investigate this, we can plot the path for one of these faulty engines. In this case, we plot the path for engine number 39. And we highlight the first and last data points for this engine and link the data points with a line to see exactly the path that the data points follow. So here we can see engine number 39 started in this region, which we assume indicates normal conditions over here, and as it was run for a longer period of time, the data points progressed outwards, and the last data point over here, where our maintenance team indicated that the engine was faulty, is very far away from this region. So our estimation is that this region indicates normal conditions. Data points in this region might indicate that problems are starting to occur, and data points that lie very far out are an indication that maintenance is soon required and that there is a likelihood of failure occurring. Now, these are our estimations for the patterns we see in the data. So now we can develop a warning system using these patterns. This image here shows a dashboard where signals have been interpreted in real time. Here we can see that the data progresses from a long time until maintenance is required to a medium time until maintenance is required until a short time until maintenance is required. And for this last bit in red, alarm is generated because maintenance is urgently required, and these last data points are actually where these engines failed. So we will use 3 categories for our data. The normal category, which implies that maintenance is not yet required. The warning category, which implies that the engine might be giving some problems and that maintenance will be soon required. And the alarm category, which indicates that maintenance should be performed as soon as possible. So we will use the patterns that we have recognized in our data to estimate initial boundaries for these categories. And here we draw up a plot with our data points and highlight these categories in different colors. So here we can see green is normal, orange is warning, and red is alarm. If we look at the path of engine number 39, as we saw in the previous plot, we would see that it starts somewhere here in normal conditions, and as it is run for more flights, it progresses into the warning category, and it would end up somewhere over here in the alarm category. Now, this was where the engine was identified as faulty, so all of this does correspond. And note that these boundaries for our categories are only initial estimates based on our interpretations of the data. So now that we have a warning system, we can look at how it can be implemented. Now, what we have worked with thus far is the data for 125 flights for all of the engines until scheduled maintenance was performed. Now we have used this data to develop a warning system, and we know that many of the engines were still in a fairly good condition at the time that maintenance was performed. So for the next time we allow the engines to run, we can schedule maintenance for after 135 flights instead of after 125 flights. But this time, when we allow the engines to run, we can use our warning system. So for example, here we see that engine 1 displays a warning before it reaches the 135 flights mark. So we can perform maintenance on engine 1 at this point, and for the other engines we can perform maintenance after 135 flights at the scheduled time. Now we have a new data set which can help us to further increase the accuracy of our warning system. So if we look at the graph of our warning system here, we can see that our boundaries are still rectangular. If we further increase the accuracy of our warning system with our new data set, these boundaries might become irregular or round shapes. Now that we have a more accurate warning system, we know that some engines are still in a good condition after 135 flights, we can schedule maintenance for 150 flights, still using our warning system. And in the cases such as engine number 1 and engine number 3, where a warning is displayed before the scheduled maintenance mark, maintenance can be performed, and for other engines such as engine number 2, maintenance can be performed at the scheduled time. Now we can continue doing this to collect more data and further increase the accuracy of our warning system until we rely purely on our warning system. So here we can see that engine number 3 is the first one to require maintenance, and once it issues a warning, we perform maintenance. Next, engine number 1 issues a warning and we perform maintenance, and so we continue. So now we never schedule maintenance, we only rely on our warning system to tell us when to schedule maintenance, and so we get maximum usage out of each engine. In a nutshell, we discussed the different approaches towards maintenance. We looked at why we use MATLAB for predictive maintenance. We looked at an example where Baker Hughes experienced a 30 to 40% decrease in costs by implementing predictive maintenance with MATLAB. We looked at what machine learning is and the different types of machine learning, and then we discussed in detail an example using MATLAB with Turbofan engine data. Now that you have seen what predictive maintenance is and what it can do, you might be wondering, how can I get this for my company? Fortunately, Optimum Solutions is the sole distributor of MathWorks products in the Southern Africa region. So Optimum Solutions can provide you with all of the tools that you need. Optimum Solutions also offers various training courses in order to equip you with the exact skills that you need to use these products. Optimum Solutions also offers consulting services which could help you to accelerate your development. The specific training path that would be required to implement predictive maintenance is the statistical and machine learning path. Now this just shows the list of courses and the order in which they should be completed in order to gain the required skill set. Firstly, MATLAB fundamentals would have to be completed in order to equip you with the basic skills you need to work with MATLAB. Then the other fundamental courses, namely statistic methods in MATLAB and machine learning with MATLAB, could be completed. Either of these courses are sufficient, depending on what your focus is. Statistical methods in MATLAB focuses on the statistics and machine learning toolbox in MATLAB, whereas machine learning with MATLAB also focuses on the neural networks toolbox. After the fundamental courses have been completed, the advanced courses can also be completed. Parallel computing with MATLAB will allow you to work with very large data sets. And building interactive applications in MATLAB will teach you how to create apps that can be used by your colleagues, say in a MATLAB environment or outside of a MATLAB environment. If you would like some more information about what we discussed today, you are very welcome to visit the MathWorks website solution pages, specifically for data analysis and machine learning with MATLAB. You can also visit the Optimum Solutions website, specifically the data analytics competency. If you are very eager to try out a few things you have seen today, you can download a free trial version of MATLAB. Optimum Solutions also provides support for licensed MathWorks product users. This is a team of application engineers and scientists which are more than willing to help you with any problems you might be experiencing. Thank you for your time. I hope you enjoyed this webinar. If there are any questions, please feel free to contact Optimum Solutions. Goodbye.